Welcome everyone to this tinyML talk. My name is Gianmarco Iodice. I am the tech lead for the ARM Compute library at ARM. And today I have the great pleasure to moderate this talk where Vitaly Kleban, co-founder and CTO of Everynet, is going to talk about low-cost energy-aware sensor data acquisition at scale. Before Vitali is going to present his presentation, I'm going to just to give you to set the scene and talk about the tinyML Foundation. And for this reason, I'm going to start talking about the strategic partners that are basically behind the tinyML Foundation. And this slide summarize all of them. So a big thank you to all of them that are making this possible, this and also the other events possible. So this definitely this is an important slide. If you are already in the Meetup group, you are aware that you can check if you have if there are talks around or near you. But if you haven't registered yet, I recommend to register to the nearest actually Meetup group to be always up to date and always aware of the tinyML talks that you can attend either virtual or in person in some regions. So, and here there are some important links. The one is definitely the Meetup link that you can, where you can see what other meetups are available worldwide. And the other is about the LinkedIn community, which is growing in the last, has been growing in the last couple of years. So let's move on to the next slide. And here, this is the slide definitely I recommend also to most of my students, because this is the place where you can learn about tinyML. This is the YouTube channel. There are more than 80K subscribers with more than 500 videos. And definitely, if you want to learn what is tinyML and all the technologies around this fascinating technology, this is definitely the right place to start. The presentation that you can find can be of different types, can be definitely technical, can be of the research type, but also can be very introductory if you don't know where to start in a tinyML space. So I definitely recommend to subscribe to the tinyML YouTube channel, where you're going to also find today's talk. Okay, so here we are, and we are almost there. Before kicking off the presentation, I'd like to introduce Vitaly Kleban. Vitaly is a serial inventor and technology architect, active in deep tech, advanced sensor and materials technology, low power and low cost data acquisition, machine learning on edge, distributed system, and telecommunications. He is the co-founder and CTO of Everynet, which is leading low-power wide area pioneer and network operator, providing innovative solutions that help companies around the world solve their biggest IoT challenges and scale quickly. It is my great pleasure to introduce Vitali. So, Vitali, you can share your screen and you can start your presentation.
My name is Vitaly Kleban. I'm Chief Technical Officer and co-founder of the company called Everynet. And today we're going to talk about bits, billions, and cents. So we're going to talk about bits of data, billions of data points, and cents that you could pay for the data point. So before we dig into the details, I would like to start from a very simple, but I think powerful model that I have in my head, and it's called systems on the chip. So in front of you, you see the rice cookers, and these rice cookers are probably manufactured, all of them are probably manufactured on one big manufacturing plant by OEM manufacturer. And what you could notice is that although all of these rice cookers are different, but the technology and the building blocks of the rice cookers are the same. So let's just take a a closer look at it. So it's two LED buttons and a button, two LED and a button, two LED and a button, two LED and a button. So the actual reason for that is the rice cooker manufacturers are trying to remove the accidental complexity of building such a device. And I believe removing of the accidental complexity is ultimately the goal of the tinyML community. So what does it actually mean? I think in 1986, the computer architect Frederick Brooks, he published a paper called No Silver Bullet, in which he actually argued that when it comes to the making of software and hardware, there were two major barriers to overcome. The first is the accidental complexity, and the second one is the essential complexity that actually comes from the domain. And if you don't have any accidental complexity, you could go from start to finish, no problem. But if you have some accidental complexity, you've had some drag that do not allow you to move from start to finish on a direct path. And the elimination of accidental complexity is simplifying the design process, deployment process, and enable big manufacturers, and it also enable big solution providers to consolidate all of the small things that our community is doing and put it together and drive down the costs, which is a very, very, very important part of the equation. So on this slide, you could see a colored version of a picture that was taken in New York in 1891. So that's the pipeline. That's a tremendous infrastructure that is still building around the human population. So the digital transformation market is growing rapidly, and it is set to reach a volume of $1 trillion by 2025. And machine learning is also quickly gaining traction and is projected to grow to volumes amounting to trillions of dollars over the next couple of decades. Such market dynamics is resulting in an immense demand for the appropriate solutions and development of this and development of the supply to match. For example, machine learning training compute resources has been doubling every 6 months for the past 10 years. So again, compute resources that are dedicated to the machine learning are doubling every 6 months for the past 10 years, basically from the, let's say, inception of the deep learning. Well, still, to this day, the lack of data is the main reason why machine learning projects and digitalization projects are failing. The problem is especially significant for the offline businesses where, ML algorithms need smart sensors to get access to the real world. And that's actually very important point, because the availability of data is often just overestimated, and the hardware is taking the bigger role in software-related processes, as machine learning algorithms and digital transformation software need these smart sensors. So if you take a sensor out of the market and you would measure the power consumption of that sensor, you would notice that the measurement and processing of the data is taking a very small fraction of the power. This is due to the fact that the computational efficiency and algorithms has improved exponentially over the past decade, while the wireless transmission continues to be energy intensive and expensive, especially at scale, especially if you want to build the sensors and ship them somewhere and make them work. So what we're going to do is we're going to focus on this wireless transmission today and try to understand how could we solve this problem. And I've tried my best to build this slide. I don't like it still, but the idea is super simple. You know, the price elasticity for the sensors is very, it really matters, right? So because the reason for that is, well, all of these IoT use cases are very price sensitive. And if you take the total cost of ownership, you would notice that, you know, you have three main components, which is hardware, maintenance cost of the sensor, and connectivity. And if you try to put together all of the kind of relationships between the building blocks inside of the sensor, you would notice that they are kind of intermingled, and it is very hard to optimize one thing without optimizing another one. And well, you have to do something with it. So the path to the profit is actually the following. You take the raw data and use some machine learning to basically compress it, to either like physically compress it or to use some embeddings to compress the data, or to do some data digest or whatever. So you compress it to the useful data, then you make sure that this useful data fits into the connectivity channel that you have. And doing all of that, you still want to be a battery power. You want to stay battery powered, because if you are not battery powered, then they probably, you know, spend much more money on maintaining the sensor. And then you want to put all of that to the device. And then I think number 5 is missing here, right? And then you go to the profit. The missing point is actually you have to deploy the sensors to the field. And deployment of the sensors is well, it's not an easy thing to do, especially the tinyML sensors. It is easy to do for the simple sensors, not easy to do for the tinyML sensors. So Everynet is basically a LoRaWAN coverage provider, LoRaWAN operator. And LoRaWAN would be impossible without the LoRa lines. This is a non-profit association that develops the LoRaWAN protocol, which is an international standard. The protocol is actually very good because it lets you create the device that could stay connected for 10 to 15 years and be like on the battery all of that time. And the protocol is very secure, it's audited, and it has the end-to-end encryption, so the users could be sure that they maintain the data ownership over the whole chain. So basically, we as operator don't have access to the data. There are flexible deployment options, which means that if there is no network, if there is no LoRa network in your area, you could build one by simply getting one of the gateways on top of the roof, or you know, into some manufacturing plant or whatever. It has very good deep penetration. It provides coverage in rural areas, including the satellite coverage, which is available like direct device to satellite. It provides the geolocation, which is a network driven. It means that you don't have to have a GPS radio on the device. You could just use the network itself to locate the sensor. And of course, it provides firmware updates over the year. And the reason for that is, of course, to limit the risk. That's the cumulative risk. The LoRa Alliance is supported by all of these companies, and it's a very vibrant ecosystem. And you could see very well-known names like AWS, Cisco, Microsoft, Bosch, Legrand, I think, and many others on this thing. So I recommend you, if you are not aware of this protocol, or of this ecosystem, just to go and take a look. Many of these people are doing sensors. Another are doing basically. They are solution providers, so they're taking sensors, putting them together to solve a particular business problem. Because if you have like a temperature sensor, then you can, do whatever you want with it. So the LoRaWAN is very interesting because, like, if you think about it, like historically, all of the wireless communications were moving towards the higher bandwidth all the time. Like currently 4G features something like 300 megabits per second download speed, right? And which is already high enough to provide all necessary bandwidth for the next generation AI. Like for the sensor, it's more than enough. But most of the sensors don't require such an enormous throughput. So what has been done with LoRa is basically you took the modern telecommunication, modern radio technology, and reduced the throughput of the network to, let's say, 300 bits per second, from 300 megabits per second to 300 bits per second. And that's enough to actually have a very useful device on the edge. So LoRaWAN is closing the gap by being energy aware and giving up device bandwidth in exchange of significantly lower device cost and much lower battery lifetime, while maintaining the network capacity. So, but device cost is a very important thing here, like pennies matter. So there are many use cases and for this oil and gas, smart metering, vaccine tracking, smart agriculture, many of them. So and all of that are publicly available on the predictive maintenance as well, by the way, on the website. So okay, LoRa can help you build a very inexpensive device, but actually to be able to connect this device, you need to have a network in place. So you could either need to build one, or you could just take something that other people are building. So this is what Everynet is doing. So we build nationwide networks in several countries. We work with the largest tower companies in each territory, and deployed quite a significant infrastructure in the field just to make sure that our customers could connect to something. So that's what we have in the United States, but also we do have Brazil, Indonesia, UK, and Ireland, and so on. So that's our available infrastructure in Brazil. That's our available infrastructure in Indonesia. I've prepared like a small thing here. That's for example, how the coverage looks like in São Paulo, Brazil. And if you zoom out and you go to the United States and you go to my favorite city here is Austin, right? So you could see that we are actually building all of these maps. We are using quite precise satellite. You could see all of the streets and building blocks and so on and so on. So these networks are ready and available for, well, for any use cases. And I'm going to tell you a little bit more about them. So, but before that, I would like to make sure that we all on the same page. So while LoRaWAN enables the existence of the low-cost device hardware, Everynet is using this spectrum sharing to actually lower the connectivity costs and increase the number of devices on the network by doing so. So what we do is we build the coverage once. So we build the coverage once, and then we sell this coverage through our neutral host technology to many actors. So, and some of our customers are Core is the biggest, I think it's the biggest MVNO in the IoT space in the world. People like Telkom Indonesia, companies like Get Wireless, Radio Wireless, NLT. So all of them are actually using our network and selling our connectivity. So on the right picture, you could see an example of the network in Brazil, where you could see 370,000 devices on the map, but the number of devices is too big to be kind of demonstrated as a thing, like, you know, as a separate points. So that's why it's like cluttered a little bit. And we put a lot of efforts to actually make our coverage resilient. All right. So which means that we are taking care of all of the gateway outages, backhaul outages, customer side outages, and Everynet cloud outages and stuff like this. So how to do that? So we do some better planning, in the sense that we are using some proprietary radio planning algorithm for to reduce the number of towers that is required to build a network. So, and by using this automation, we are reducing the number of towers that we deploy. We increase the quality of installations by taking control over the all quality control procedures, all of the installation. We provide specific like mobile applications for the technicians and so on. And our networks are operating, you know, basically Everynet is building this nationwide networks that includes thousands of gateways that are located in a very challenging environment, tropical environment. For example, on the picture here, you could see Hurricane Fiona hitting the Puerto Rico, and actually this network survived the hurricane as well. So, and we just need to make sure that gateways are designed to help us build reliable carrier-grade networks, and this is what we do. Well, our offering is quite simple. So we offer a fully managed field infrastructure. So if you have a device-related project and you want to deploy devices, you don't need to be worried about the field infrastructure for the network. It would guarantee you the cost reductions, and 60% is a very pessimistic, actually, number. It could be much higher. And we provide detailed, proactive densification planning. So because we have access to such an enormous infrastructure, we could assure you that we would densify the network faster that you are deploying devices. So it is always the case. So sometimes customers are worried that, okay, I don't have a network in that particular point, like a village, for example, but still it's possible to get that coverage very, very quickly in case of Everynet. So here is an example of the difference between the tower installation and the let's say customer-based installation. So what we noticed is that from our experience, the customer-owned sites provide less less link budgets rather than professional tower operators. So customers are basically using much more gateways, and at scale, when we are talking about hundreds of thousands of devices, we would not recommend to rely on, well, let's say self-made private networks. On this example, I could show you it's basically a leading gas utility in Latin America. They deployed 70,000 meters in 2021. They have an almost 1,800,000 plant in 2022, 2024. And we are getting 95% of all of the meter readings. It's a very high number considering the fact that they are located in a very, very dense urban environment. So, and of course, that was the early days. And later, after the densification, we increased this 95% even more. But again, thanks to LoRaWAN and thanks to the availability of our infrastructure, we can actually, densify these networks up to the point where even in a super dense environment, we could get all of the necessary devices covered. And what also is good is that the contracts we have typically with the device manufacturers, because the battery lifetime is so long, we are automatically getting the contracts for these are evergreen contracts for 10 years with a 10-year commitment for network to survive. So, coming closer to the tinyML thing. So, as I said, I would say that low-cost connectivity and tinyML are very, very, they play very well together. And for example, there is this device called Bob Assistant. I actually like the device itself. And the idea of this device is pretty simple, right? That you could take a vibration sensor, you could train it to, or you could put it, well, not so simple, but you could put an anomaly detection algorithm on it, and you could apply this sensor to practically anything that vibrates, anything that has a motor inside. And if you take a city that is big enough, if you take a city like Berlin, it probably has, as I remember, it has 2 million water pumps in it. So it's automatically a 2 million sensors project. So, and this sensor is, I think, it is readily available, and it is using some machine learning, and it is using LoRaWAN to back all of the data. So, but at the same time, tinyML on low power, low cost sensors is a very challenging thing to do, because there is no good answer, about what's going to happen after the fit predict cycle. And for example, we need to know how to collect the raw data, because the raw data is not available. Like, okay, you could collect it for your for the initial training, but what to do next? Because your model is going to suffer from distribution shifts, from the covariance shifts, or whatever. How to identify model retraining intervals, how to run A/B tests. You have a fleet of devices, hundreds of thousands of devices. How do you run A/B tests? How do you do shadow or canary deployments? How do you assess the results? So, the cold start problem, the fallback, and how to do the on-device model evaluation, something that you could afford on a bigger computer, but how do you do this on device? And hopefully the tinyML deployment work group can create a vibrant community of practitioners that could solve these problems. So, for example, like I took this example of Bob Assistant, and I actually don't know how it works inside of this particular sensor, but you might think about the following things. So, if you could afford a continued on-sensor model evaluation, then you may have a fallback model. Like in the best scenario, what you have is you're doing this processing or ML on device. If you can't do this, so if you notice that your model is not performing anymore, you could switch to just data compressing. If you can't do data compressing anymore, for some reasons, you could just switch to the data collection. Or what you could also do, if you have all of these three modes available in the device, you could randomly switch between them for one purpose, to collect more raw data. So all of these questions are open, and I'm happy to discuss tinyML algorithms deployment options for this low power, low cost devices, and consider joining the tinyML deployment work group and LoRaWAN's technical committee. Feel free to connect, and I'm happy to take any questions.
Okay, thanks a lot, Vitali, for the brilliant presentation. So probably I can share my screen now. But before that, okay, perfect. Thanks. Let me share my screen. Okay. So let me see if we have any questions. Okay, we don't have questions yet, but I do have one. It's about the physical range for this communication. What is the order for the physical range? Are we talking about kilometers? Are we talking about meters? What kind of physical range do we have for LoRaWAN?
So, of course, like there is a theoretical physical range or in the open space, right? And it's some hundreds of kilometers. Wow. And and it has been proven that the practical range is actually not very different from the theoretical one. So if you put a transceiver on the helium balloon, right, then you're gonna get very close, like hundreds of kilometers of communication. But when you go back on Earth, right, so you have your tower and you have your device that is somewhere. It all depends on where you are. If it's a city or if it's a rural area. In rural area, the distance is 10 plus kilometers between the device and while keeping it all low power, all right? So it's like 25 milliwatts of output power for device. So, and in the city, it could be from 1 to 5 kilometers, depends on how dense the city is and how good the radio is there.
Okay, and I guess this will affect the density of how many devices you're going to deploy in a specific area, I guess, right? Because if you're saying that in the rural area, they're going to have probably a physical range of, let's say, 10 kilometers, as you said, probably we will need fewer devices compared to a city. Is it more or less correct what I'm trying to say?
That's right. So if you take a look at the deployment options, the city are always has more, like, let's say, base stations that we have to deploy than the rural things.
Okay, that's perfect. So that a couple of questions. Okay, let me go to the one. How can existing IoT devices that run AI on board use LoRa?
Right. So, of course, we are not talking about training of model on board of the device. In most cases, what we are talking about is the evaluation of a pre-trained model on a low-power device. And this has been done, I think, many times by, I mean, there are even some implementations of neural networks in silica already. I think there are a lot of materials on the tinyML community on how exactly to do this thing. Okay. So because LoRaWAN devices are using the same microcontrollers, microprocessors that the normal devices.
Okay, thanks for the question, but also for the answer. There is another one. Is it possible to build a LoRa network as a mesh protocol?
Well, I think technically everything is possible. But there is no actual reason to do that in a way that mesh protocols are very hard to manage at scale. Like if you have 1 to 10 devices that are, communicating via mesh, that's all right. But if you have hundreds of thousands of devices, then it becomes very, very hard to manage. So the answer is technically yes, you could do this. That would not be LoRaWAN, probably. That would be some let's say, DIY protocol. But using the same physical principles, you could actually do the mesh network, yes.
Okay. So I have some other questions, if I can. So I'm curious about you talk about the power consumption. How it is, what is the ratio in terms of power consumption, for example, compared to a Bluetooth communication? A ballpark number.
Yeah, so I think if you take a look at the Bluetooth, so Bluetooth is so efficient right now that the battery self-discharge is almost equal to the device power consumption. Like if you are sending Bluetooth beacon like every hour, the battery would probably die from the shelf life, not from the fact that it was drawn by battery. So of course, LoRa do have more power consumption rather than Bluetooth, but it is, again, so small that you could build a device that could last for 10 years on the battery, where 10 years is actually the limitation of the battery, not of the device power consumption. It's a battery shelf life. It's a battery chemistry that you cannot beat.
Okay. I suppose also the physical range will change. Probably Bluetooth is a bit shorter compared to LoRaWAN, probably.
Yeah. Yeah,
Okay.
but Bluetooth was built for a different purpose, right? So it was built to actually have a communication from, I don't know, your phone to your earpiece, whatever. So, but LoRa is for different purposes. It do not have as many features, I would say, as Bluetooth, well, because Bluetooth has all of these profiles and things like this. But at the same time, LoRa is designed to actually provide a ubiquitous, coverage like everywhere, and that's what we are focused on.
Okay, thanks. So there are no other questions, but well, definitely I have a lot of questions in my head, so it's not a problem. So, well, actually, this is not a question, but probably a consideration. So one of your last slide is about trying to meet the tinyML community to exploit possible applications in this domain. One possible, I don't know if it is a crazy idea, but for me, the hierarchical approach is something probably applicable. In one of your slides, for instance, you show collect raw data and transmit, collect raw data, compress and transmit, collect raw data, process and transmit. Definitely the takeaway from this presentation is compute as much as you can, transmit only what you need. Therefore, what you think about aggregating the results of nearby nodes, for example, to extend the lifetime of the overall network in general? What I'm trying to say is, could their devices communicate with a very low power communication product like Bluetooth to exchange data, aggregate the data, and maybe transmit only when something different change in that local region? What do you think?
Yeah, so it is definitely possible, but not very viable in terms of the scaling. So the reason for that is that the customer would have to manage, an additional layer of infrastructure. And sometimes it becomes very, very complicated, especially when the installation is very big. So the beauty of LoRa in this case is that you could actually collect information from as many sensors as you want and still be on a very low power side. So you don't have to invent things like, I don't know, hubs, repeaters, whatever. So you could put a LoRa chip in your sensor and just that's it.
Okay, thanks. So basically, complexity is one drawback of what I just said. Cool. Thanks, Vitali, for answering my questions. Are there any other questions from the audience? Meanwhile, is there something else you want to highlight from your presentation that you would like to share with the attendees?
So the whole thing is, the whole idea of my presentation was to actually make sure that the tinyML community is aware of the LoRa technology, is aware of the presence of the networks. Unfortunately, I can speak only about the networks I own and operate. So that's why it looks like marketing whatever material, but it is not. So and I would say that the tinyML model training and evaluation is not that different from the big machine learning training and evaluation, but the lack of raw data available, for the model retraining is the biggest challenge right now. So I think that in general the engineering community knows how to train and run the model on the device. What is not known is how to actually devise it in on how to actually deploy it at scale. That's the problem. So, because when it starts to deploying stuff, there are trillions of problems. There are trillions of, customer issues, whatever. So millions of things that just need to work.
Thanks a lot. Thanks a lot, Vitali. It was absolutely a pleasure. But before closing this tinyML talk, I'd like to thank again our strategic partners making this tinyML talk and other initiatives free and available to everyone. So thanks a lot to everyone behind the scene that actually making this possible. Here I'm going through the list of strategic partners, the execute strategic partners, which are Edge Impulse, the leading development platform for Edge ML, Qualcomm AI for advancing AI research to make efficient AI ubiquitous, Sentient. We're making Edge AI a reality. Now it's the time for the platinum strategic partners. So Deployed for fastest video analytics solutions on CPUs. Click Attack, global IoT solutions. Renesas, who is enabling the next generation of AI-powered solutions that will revolutionize the every industry sector. Sony Semiconductor Solutions Corporation. In terms of gold strategic partners, we have Analog Devices, where what if becomes what it is. ARM, and here I recommend to sign up for our ARM AI virtual tech talks based on ML. Photo Hub, by making over the air framework and ML models updates simple and accessible. Microsoft, NXP, together we accelerated breakthroughs that advance our work. SenseML Analytics Toolkit Suite. ST Microtronics provides extensive solutions to make tiny machine learning easy. Synaptics, engineering exceptional experiences. And here's the list of silver strategic partners, AZ, Aeon and Devices, ENSA, Greenwaves, Gravity, EBM, ImageMob, Itemis, NorthAI, OctoML, Privacy, Quixo, Rixen, SAP, Silicon Labs, Stream Analyze, and TDK. And before we finish, just a reminder about our upcoming tinyML talk, the 13th of December. Mahesh Choudhary, the fellow and senior director of MEM software solutions for ST Microtronics, who is going to talk about smart motion sensors that offers a world of always-on possibilities. This talk will be around the use cases and the applications of always-on solutions. And that's it for today. So with this slide, I'd like to thank you again, everyone, for attending this talk, and definitely see you next time. Bye-bye.